Okay, so let me pass on to climate change then. So I'd like to begin this part by citing a very famous economist, John Maynard Keynes. I'm not sure he actually ever wrote this down somewhere, but he certainly wrote about the themes. And that is that for millennia, until the Industrial Revolution, the only way humans made economic progress was to enslave other peoples. Think about that. For millennia, the only way we made progress was to enslave other people, people of other races, children, women. Okay? And here is a plot showing Great Britain, where the Industrial Revolution took place from 0 AD to about the late 1800s. You know, people basically lived at a level of several $100s a year, namely about $2 or less a day. And then came the Industrial Revolution, which basically was powered by the discovery of coal and the harnessing of machine power to substitute for human labor. Later, oil and now natural gas is making the same substitution. And then per capita income took off in constant dollars until today in Great Britain it's more than $25,000 a year. Okay? What I'd like to remind people is that the Industrial Revolution has not come to 2 billion people in the world. There are 2 billion people in the world that live on less than $2 a day. We can talk about conservation in the rich countries. We can use less. That's definitely true. But how do you tell people who are living on less than $2 a day that they need to live on less? Don't they have a right? Don't they have a right to aspirations for a better life? That is the fundamental problem that this problem raises globally. Now, of course, we also know what the environmental cost of the Industrial Revolution is. The Industrial Revolution was great. We should not demonize fossil fuels when we think of all the benefits we have gotten. But unfortunately, like most solutions, eventually problems develop from the solution. And that problem is, of course, the increase of greenhouse gas in the atmosphere. So what is the greenhouse effect? It is simply this fact that the atmosphere of the Earth is a blanket. It's a blanket to which visible radiation is transparent once it gets below the clouds. It heats the surface of the Earth, which re-radiates this radiation in infrared radiation. And the Earth's blanket is not transparent to infrared radiation, and therefore traps it. Same way that when you want to get warm at night, you get in bed, you put a blanket over yourself. When you put that blanket over yourself, your metabolism is not increasing. But because there is a blanket above you, to push out the same amount of heat, the bottom has to get warmer than the top, which is at the temperature of the room. That's a simple greenhouse effect. There can be no argument about it, or even the magnitude of the effect. Theoretically, it's about 60 degrees Fahrenheit on average. Well, that's just a statement, you know, outside it's pretty comfortable. You get to the top of the mountains, it's below freezing. You get above that in an airplane, it's well below freezing. That's the 60 degrees Fahrenheit. Okay? So there's no argument that this is happening. Well, so how much of the blanket is carbon dioxide? We know that from measurements. It's 27%. 27% of 60 degrees Fahrenheit is 16 degrees Fahrenheit. So here is the carbon dioxide level plotted since a little after the last ice age to the present day. So 10,000 years worth of data. And at no point until the beginning of the Industrial Revolution has the carbon dioxide level exceeded 280 parts per million. And then over the last 200 years, roughly, it shot up to where it's today. It's 392 parts per million. So 16 degrees Fahrenheit is what 280 parts per million brought. It's a simple calculation, if you have a calculator, that at 392 parts per million, it should be a little more than 22 Fahrenheit. which is a change in temperature of 6 degrees. But in fact, we've only seen 1.6 degrees Fahrenheit. And the reason for that is we haven't come into equilibrium. When you get under that blanket at night, it doesn't instantaneously become warm, right? You have to warm up the blanket and put out the bed sheets. The same thing is true in the case of the Earth. We're not in equilibrium yet. And the reason is because of the ice in the world. So if I had a glass of ice water here, okay, you all know, even though more heat may be put in than is being radiated out, the temperature doesn't go up. It goes into melting, the heat goes into melting the ice. To a physicist or a chemist, goes into releasing the latent heat, okay? Only after the ice melts does the temperature begin to shoot up. That's what we are doing in the world. We are living on borrowed time by melting the ice of the world. Now here's a plot of the temperature change since the Industrial Revolution. This made the news this year because my colleagues at Berkeley who doubted this remeasured everything and got the same result as everybody else. So of course now we can believe it, right? Okay. And you can see it's only been about 1.6 degrees. Now some people argue, well, you know, the last 10 years it's been pretty flat. Maybe climate change hasn't happened. Even if we're perfectly flat, it's happening because we're melting the ice. You can see that, okay? In fact, climate change is not defined as 1 year or 10 years. It is defined, climate, as 30-year running average. Over 30 years, you can see the trends. Okay, so when we look at pictures of the polar bear and the ice is dwindling around him or her, think not that it's a polar bear. It's your children. It's your grandchildren. We are living on borrowed time. When that ice is gone, the temperature will shoot up quickly to that full 6 degrees Fahrenheit. In fact, not only will the temperature shoot up, but if this were a bottle of Coke, okay, when the ice is there, the carbon dioxide stays in the Coke. When the ice is gone, the fizz comes out. There's more carbon dioxide in the oceans than in the atmosphere. That is the danger that faces us. Now, you can say, well, how long is this borrowed time? We know how much extra heat is being put down. It's been measured by satellites. It would take about 1,300 years to melt all the ice. Okay? Oh, that doesn't sound so bad. But only 10% of that ice is in the northern hemisphere. And half of the heat comes into the northern hemisphere. So you reduce that by a factor of 5, it becomes 260 years. So by the middle of the 22nd century, all the ice will be gone in the northern hemisphere, including Greenland, which will raise sea levels by 6 meters. Okay? When the ice is gone from the poles, that will be just maybe another 40 years. Some people say as early as 2030, the summer ice will be gone. When the ice is gone in the poles, do you think there will be much snow in Sierras? If there's not snow in the Sierras, what do we do about drinking water? This is a very serious problem. We don't have 1,000 years. We don't have 200 years. We may have 40 years, and in 40 years, we may not even have that because fossil fuel plants are being planned today, and once they're built, nobody's going to tear them down for 40 years. So we may have 5 to 10 years. That's how serious the problem is. So let me give this slide to explain why it's hard to beat coal or gas for turbine electricity generation. The only thing you need to accept here, and physicists or chemists can tell you these numbers are accurate, that is how much energy does a kilogram of coal, or for that matter, 0.6 kilograms of oil contain? The answer is that it has the same amount of energy as 0.5 milligrams of uranium or thorium. That's a statement that the atom has 1,000,000 times more energy in its nucleus than in its electronic shells. And how much more energy does that kilogram of coal have than, let's say, wind? Well, 1 kilogram of coal has enough energy so that it equals 1 million cubic meters of wind at 25 kilometers per hour, about 15 miles per hour. Okay? That's just a simple statement that the electron in orbitals around the atom or molecules goes at about 1% the speed of light. Wind doesn't go anywhere near that. Okay, and you have to square it when you consider the energy. So when you work it all out, even considering the electrons, much less than the atom or the molecule in weight, it's millions of times more. That is why a few liters of gasoline in your car can power you, for 60 miles. All right, at 60 miles per hour, much faster than the wind. All right, but what does that have? Another implication. Well, the way we generate energy today is we burn something in a boiler, we heat up water, it turns into a gas, that gas expands, it goes past the turbine turns, if it has a magnet and turns past coils of water, we get alternating electricity. But the fact is that chemical energy is 1 million times more powerful than mechanical energy at ordinary speeds, means is that the turbine part of a power plant is much bigger than the boiler or the nuclear part. That's why it's so hard for nuclear to beat coal, because the big part of the plant is the same. It doesn't matter that the small thing is much more efficient or much more energetic. The big part is the same, so it's hard to beat. It still should be cheaper, but for historical reasons, it's been driven so that by other external forces, so it becomes more expensive. Turning it around, if I want to use wind to turn this turbine, I need to build huge things. That's why these windmills, have arms that are as big as a whole power plant, and you need thousands of them to equal what a coal-fired power plant becomes. Another way of expressing this is, if you've ever seen the large wind farm in California, there are hundreds, several hundreds, on thousands of acres. Okay? They only put out, average, the same amount of energy as one Boeing 747. So 4 little tiny engines produces the same power, simply for that reason. Okay? So how do you make something like that competitive? You can't. All this talk about things going down, it's not going to happen. If there are improvements in turbine technology, the fossil fuels will use it too. Okay? Natural gas has an advantage because it's already a gas. You don't have to heat up water to turn it into steam, which is high corrosive. You just heat it up and it expands. You go past a turbine, it can create very fast wind. Jet turbine is an example, okay? So gas turbines are so cheap. They're fast to build. Everybody's building them now. If they keep building them, forget it. The game is over. Plus, the waste heat can come back down here and be used in a so-called combined cycle that gives greater efficiency. So basically, it's hard to beat unless you go in a different direction. That's why I think that we should go into use nuclear fission and use it for, at least to begin with, for its process heat, not to turn turbines.